In this module, we'll discuss the different kinds of nodes, blockchain network structure, and how conflicts are resolved in a permissionless setting. In blockchain systems, not all nodes are the same. Under the broadest definitions, any machine that interacts with the network in some way can be considered a node. So far, when we've talked about nodes, we've been discussing full nodes, nodes that have a full copy of all the blockchain's transactions. When a full node receives a block, it will perform checks on the contents of the block, including the timestamp, hash, and difficulty. Amongst other things, it must verify each of the transactions on whether the inputs have previously been spent, whether the signature matches the public key, whether the sum of the inputs is greater than or equal to the sum of the outputs. If it's satisfied, the node will keep a copy of the block and propagate it to the rest of its peers. A full node is the best way to get an accurate image of the blockchain. Without one, you need to trust a third party to feed you the data you need. But because they download, validate, and store all of that information, they might not appeal to everyone. The Bitcoin blockchain is over 400 gigabytes as of mid-2022. Nodes download and validate blocks at 10-minute intervals. To some, this may be a strain on storage and bandwidth. On the other hand, light nodes are devices that connect to other nodes, but perform limited validation on the data. Because of this, they have lower storage and bandwidth requirements, and can be run on devices such as cell phones or low-end computers. If you use a non-custodial wallet, that's most likely a light node. Instead of downloading full blocks, light nodes download only the block headers, which are much smaller in size. The block header gives you important information such as previous block hash, timestamp, and other metadata. Ultimately, light nodes rely on full nodes to operate. Then, there are mining nodes. Technically, mining nodes are either full nodes or light nodes, but these are a subset of nodes that perform the proof of work necessary to secure the network. For cryptocurrencies like Bitcoin that use proof-of-work consensus mechanisms, a simple computer isn't enough to perform the hashing operations. Because there's so much competition in mining, specialized machines must be used. Examples include GPUs, as you might find in gaming computers, or purpose-built devices like application-specific integrated circuits. We say that public blockchains are permissionless and anyone can become a node. You might be wondering, with nobody in charge, how can changes be made to the network? In a truly decentralized network, changes can be made with soft forks or hard forks. A hard fork occurs when you want to introduce changes to the software that make older nodes obsolete. The network is effectively fragmented into two parts, one made up of old nodes and one made up of upgraded nodes. The two can't communicate. For all intents and purposes, there are now two networks. Soft forks are upgrades to the network that are backward compatible. Certain upgrades can be added in a way that doesn't interfere with the regular functioning of the network. For instance, a block size reduction. A soft fork might be preferential in scenarios where you don't want to divide users into different camps. In effect, the upgrade is considered opt-in. Certain newer features might be invisible to you, but you can still communicate with the upgraded nodes. Whew, that's a lot we've covered in the first 5 modules. In the next and last module of this course, we'll go over blockchain use cases and its limitations.